So I'm Sean Parent. As he mentioned, I work at Adobe Systems. I'm a principal scientist there. I just a few months ago kind of rejoined the Photoshop team. I'd been away from Photoshop for about 15 years, but I'm back working with the Photoshop team. I've been at Adobe, depending on how you count, about 22 years. So a long time. It depends on how you count, because I left after 15 years for a little over a year and went to Google to work on Chrome OS. Before Adobe, I worked at Apple in the system software group for about 5 years. So I've kind of been around the valley for a long time. One of the best jobs I had in my entire career working at Adobe, I ran Adobe Software Technology Lab. And that meant that I was Alex Stepanov's boss for about 8 years. So for people who know who Alex Stepanov is, he's the guy who created STL. And just an absolutely brilliant and wonderful individual to work with. This talk came about because I got invited to give a keynote at ICPC, which is the International Conference for Program Comprehension. I didn't know a lot about program comprehension. I knew there was a field in computer science that's program comprehension. So I thought it was an odd choice for a keynote, given it's not my area of expertise. But for people who don't know, the study of program comprehension is the study of how you approach a code base and understand the code within it. Okay? So there's kind of a whole field of computer science and people publishing papers in this space. So not knowing a lot about it, well, this is outline for a bunch of talks that I've given. You can find most of these online. This talk is somewhat an overview of some of the material in these talks. And this all started because a few years ago I gave a talk that was very well received at Microsoft, and that's spurred me to try to write a book, which may never happen, but or I'll retire and then write the book. But it's a slow work in progress. So in any case, back to program comprehension. I thought I would at least ask around how people who I work with, who have a lot of experience in jumping into big code bases, how do they come to understand a large code base, and how do they come to think about it? And although we're not going to talk all about program comprehension here, I think it's a good jumping off point in thinking about how you come to understand a large code base, to think about how you write better code. And that is the topic of this talk. So how many people here know what the knowledge is? 2 people. So I was just in London like last week I gave 2 talks in London. Yeah, somebody else knows now as soon as I say London. I was in London like 2 weeks ago and I gave 2 talks, and I didn't give this talk, which is unfortunate. But the knowledge is the test that cab drivers in London have to take before they can drive the black cabs in London. And it's considered one of the most difficult tests to take for any cab driver or for almost any public servant. And people spend years studying so that they can pass the knowledge and become a London cab driver. And basically, in order to pass the test, you need to be able to not only know where all the landmarks in London are, but you need to know the history so that you can entertain the people who are riding in your cab and tell them about the history of the landmarks that they're passing. You need to know the quickest route from any hotel to any landmark, and any landmark to any hotel, and from any hotel to any other hotel, and to get to any of the various airports around the area. So a lot of studying goes into the knowledge. And I think there's a parallel to how people understand code. When I ask people, how do you come to understand a large piece of code? A lot of people would say, well, I will trace through the code following what happens to some piece of data as it goes from point A to point B, right? So that will light up a little piece of the code for me. And other people said, well, I will just start in one area of the code, and I'll kind of look around at all the inputs and outputs to this area, and I will try to just understand one piece of the code really well, and then I can use that to start branching out. Okay. And some people said, no, I will take like a module that has like clearly defined edges, and I will understand how that module works. So this is a bureau of London there, rough outline of a bureau in London, right? So I will take a module and understand that. And when I thought about it, I thought, this is interesting. And certainly, I think everybody uses these techniques in one way or another when they're learning a code base. But this isn't how I think about learning a large code base. Okay, this is how I think about learning a large code base. How many people know what this is? Hopefully everybody, right? Right. So this is a map of the London tube system and the London trains. It's a logical map. Okay, this is not a geographic map, right? And what do I mean by that? If you overlay that map onto a map of London, it looks like this, which is a very different thing. Okay, so when I study a code base, I'm interested in getting to this. Right, which is not the actual structure of the code, it's an idealized structure of the code. Okay. So, to get there, the first thing you have to understand is there are rules. Right? What do I mean by that? How a piece of code works is governed by rules, by mathematical rules. So this is a function out of STL called lower bounds, right? And you can read through the code here. It's a form of a binary search, right? Finds the lowest position at which you could insert an element to maintain the ordering within a sequence, okay? But in order for this piece of code to work, there's a lot of requirements on this piece of code, right? We have a forward iterator, first and a forward iterator last. Well, those two iterators have to denote a valid range. Okay? So, which means last has to be reachable from first just by incrementing first. Okay. We have a comparison function here, right? That comparison has to implement a strict weak ordering onto this sequence. Okay? Or lower bound will fail to work. Okay? When we dereference our iterators, they have to give us a type that's comparable to our value type, the value that we're searching. Okay? So there's a lot of requirements in this code, a lot of rules that govern whether or not this piece of code is correct that aren't necessarily directly in the code itself. Right? So in order to understand this, you have to understand what those rules are that sit around it. Now, when I approach a large code base, and most of what I work on is desktop software or mobile software or things of that nature, right? I tend to approach it from the outside behavior looking in, right? So this is actually a menu clipped out of Microsoft Word, not an Adobe product, right? And what's the first thing that you might notice about this menu? Okay, anybody? Yeah, some things are active and some things aren't. Okay, so when I look at something like this, the first thing I think is not, well, where is the code that sets some bit to say whether or not this thing is active? I want to know what's the rule that governs whether or not a thing should be active or not. Okay. And so I start to build up a mental model of what a menu item is. Right? And I say, well, a menu item has some predicate that's associated with some function. Okay? So that's associated with a menu item. So you get a structure like this. What do I mean by that? Well, what is a menu item? When you pick it, it's some function, it's some command that you're going to execute. Right? And that menu item is enabled or disabled. Why would I disable a menu item? Why would I not want to call some function? Anybody? Okay. It's not applicable. What's another way to state that? Right?
User expectations.
User expectations. So there's a much more mathematical notion.
Preconditions aren't met.
Preconditions aren't met. Okay? So what I've got is I've got some function associated with some menu item, and I can't invoke that function because the state of my system doesn't satisfy the preconditions. Okay? Well, that means that there's state somewhere that's feeding into this. Okay? So I've got some state that's feeding into both my predicate and my function. Okay? So, and now my menu item is acting as some kind of latch to go trigger that. And then my function is going to execute and probably go update my state. Okay? So when I'm looking at this, I've got some issues, though. The state is feeding to both my predicate and my function. Okay, that's kind of a logical split, right? When I'm dealing with the desktop system, that means that now I've got a potential consistency problem, right? Right? Is the state that's feeding my predicate really the same state that's feeding my function? And if I'm dealing with a threaded system, I have to make sure that those two things are logically consistent. Okay? So what I really want to do is untangle that. Okay? An M there, because that's a form of a monad if you're a functional programmer. Okay? It's a Kleisli category. What we want to do is we want to say no. What we want is we want to take the state, we want to feed that, okay, into our predicate, evaluate the predicate, decorate the state with the predicate, feed that to the menu item. Now the menu item can just act as a latch, right, like a switch in a circuit or a valve in a pipe. And now the information can flow from my menu item into my function. My function can do what my function needs to do, and that generates a new state, my state prime. Okay, so now in my head, I've logically flowed this thing out into a functional form that I can reason about, and I can think this is correct. Okay, so this is my abstract idea of what a menu item is. Right? And for this to be valid, I got the little dashed line there between my M and my F. That means that this predicate has to be a valid corresponding predicate that matches the preconditions of my function. So there's a relationship there. Okay. So that's how I think about this behavior. Now, when I form that mental model, I'm under no illusion that any application is actually written that way. Okay? I work on a whole bunch of applications, and they have model view controller this, and MVVM that, and some pattern of some structure in how this thing comes together. Okay? But by forming a mental model of how it's supposed to work, now when I go and I read the code, right, I can figure out basically where I am in the city. Right? What's the purpose of this piece of code? How does that map onto my ideal model there? I know that everything that's in that ideal model has to exist in the code if the code's correct. Okay? So having the ideal model gives me the roadmap to understand the rest of the code. And now I don't have to understand how any particular menu item works. I just have to understand, well, I've got my map. I know that this map exists everywhere. And if I'm looking at a piece of code, maybe I'm looking at a bug, this thing is not enabled when it should be enabled. Now I've got a way to figure out, okay, well, this is how it's supposed to work. What role does each piece of code here play, and where do those assumptions go wrong? Right? Is my predicate not a valid predicate? Is it the state didn't carry through, so I've got a discrepancy in the state. My predicate's evaluating on one state, but my function's executing another. Right? What went wrong here? So good code. Good code is correct. Right? What do we mean correct? We mean correct in a mathematical sense. Good code is consistent. It's without contradiction. Right? So let's think about a piece of code here. I wrote a piece of code with a bug. Very obvious bug. What's the bug? What's that? Dereference null, right? I'm calling print string with a null pointer. It's about to crash. Right? If I execute it, that's what I'm going to get. Bad access right there. Okay. But what's the bug?
Looks to me like there's an extra dereference.
There's an extra dereference. Well, there's a dereference, right? Right. So we got the dereference there. It depends. It depends. Maybe there's no bug at all if I just put the comment in here. It says force crash. Okay. Okay. So what we have is we have some assumed intent by reading the code, right? And that's a valid thing to do, right? And if you speak with people in a university, they will frequently say that a piece of code is correct if the piece of code matches the specification, okay? Well, if the piece of code does not match the specification, that doesn't necessarily mean the code is wrong. It could equally as well, and in all likelihood, the probability is much higher that the specification is wrong, right? Because our definition of correctness is that our system is consistent, okay? Which that means that the specification is consistent with the code, and if you have test cases, consistent with the test cases. So it's like double entry bookkeeping. If you write things down in multiple ways, okay, then if you make a mistake along one way, you're more likely to catch it, right? So the purpose of a specification is to help us catch a mistake, right? Right? Now this code, even though I fixed the specification and said I'm forcing a crash, is still wrong. Why is this piece of code still wrong? It won't necessarily crash. It's undefined behavior. Okay? Okay. So what does that mean? That means that I said force crash, and then I went through this, and I've got an inconsistency. I've got an inconsistency with the specification of the language that I'm writing the code in. Okay? So this code is still not correct, and that's where the inconsistency is. Okay? So consistency requires context, right? So let's take a look at another example. This is the definition of min, and this is the definition of max. And these are somewhat abbreviated definitions, but they're both out of the standard. So I would contend that the definition of max is wrong. Why? They're not symmetric, right? Right? I have this quote that's like floated around Twitter a lot, and people always ask me about it. Where I say good code is clean and symmetric. Okay? I actually say I think clean, simple, and symmetric. So people always say, what do you mean by symmetric? Okay. Well, here's a case where it's asymmetric. Okay, and what's the problem with that? If I were to ask you, what's the maximum of two things that are sorted? Okay, right? If I said, what's the maximum if I have two things and they're sorted, what's the maximum item? It's the second one, right? Or if I have a set of them, it's the last one. Okay, and the minimum is the first one. Two things are sorted, right? If I pass you two 4s, well, that's sorted. So what's the maximum of two 4s? It's the second 4, right? Right? But this will return the first one, okay? And you might think that that doesn't matter, but it's returning it by address, okay? So it actually does matter. And it leads to subtle defects. I don't know how many times in product code I've seen people write this, right? Frequently they won't even put it in a function, but I'm putting it in a function here because there's now a proposed or possibly standard function at this point. It's in? Yeah, so there's a clamp function, right? So if you wrote std clamp like this in terms of std min and max, and this is the natural way you would do it, right? You have a low value and then the value you're clamping high, right? So what we're trying to do is we're trying to clamp A between low and high. Okay? And this comes up in graphics all the time. Okay? You clamp values in graphics all the time. And that's the natural way to write it. And it's wrong. Okay? It's wrong because our max is wrong. Right? So here's a way where we can see it. Well, another form of clamp would take your own comparison function. So let's say I had a piece of code like this, right? I'm only comparing by the first member, and I want to clamp between a low and high. In this case, here's my low, here's my high. But I'm only comparing the first members. Okay? And if the thing is outside of the range, then I want to know because I'm going to return the clamp value and not the value I'm trying to clamp. Right? So that's going to print fail. We were outside the clamp, even though we weren't, because 1 is equal to 1. And we picked the wrong one. Okay? So you have to write clamp this way if you're using the standard functions. Right? Yeah, these are things people don't think about. These are things that keep me up late at night. I'm a strange person. You know, and then you would write the clamp with the comparison function that way. Okay. So this is what it should be. Returns the second argument when the arguments are equivalent. Right? Right? And if you start to say, well, what if we had max of 3 items or max of some variable number of arguments, okay, then the problem just gets worse, and it becomes more important that you do the right thing. Right? So here what we want to say is to say that if they're in sorted order, you get the last one, right? Now, one difficult thing about rules is rules are contentious, okay? People argue about what the rules should be, right? This is a quote. I've put this in a few of my talks, and I'm somewhat picking on Craig. Craig was a very early employee at Google. And during the brief time that I worked at Google, like 5 years ago, Craig was in charge of the coding guidelines. And although I think Google's coding guidelines have gotten better, I still think they're pretty horrible. And coming out of when I went from Adobe to Google, it came out of me running their software technology lab. So at Adobe, I somewhat had the same position that Craig had as head of the software technology lab. I had the equivalent position at Adobe. So Craig and I did not see eye to eye and had some very boisterous and public arguments about code. And this was an email that Craig sent not just to me, but it was on a mailing list. And so I'm probably violating some Google rule about disclosing this. But take a moment and read this, okay? Names should not be associated with semantics. And you can just put a dead stop right there. How do we communicate, okay, if we strip nouns of their meaning? Okay? What does that even mean? Right? You can just stop right there and go, he succeeded. Yes. Okay. And what he's saying is because everybody has their own hidden assumptions about what semantics are, and they clash, and that causes comprehension problems without knowing why. This is why it's valuable to write code to reflect what the code is actually doing rather than what the code means. Okay? It's hard to have conceptual classes about what code does. I disagree. There is no spoon. Right. So here's a place where we frequently end up with conceptual classes. Right? How can nothing be something? Right? In C++, this manifests itself in a lot of ways. So what is int of x? What's the value of x? Undefined. Indeterminate value is what the standard says about it. What's that? Well, this has to be a local scope. Okay? It's an indeterminate value. What about that? Ooh, come on, quiz time. Somebody? Undefined behavior. Okay, which is different than an indeterminate value, by the way. What about this one? What's that? Then defined, yeah. It's actually defined in the standard. It's infinity. What about this one?
Nana, that's definitely not a number.
That's definitely a nan. Okay. Empty struct, completely fine to declare. But the size of an empty struct is 1.
Yes, that is correct.
Okay? Why is the size of an empty struct 1? Everything needs to have an identity. Everything needs to have a unique address. So size of it has to be non-zero, so it's defined to be 1. Okay. What about a 0 size array?
Syntactically invalid.
That's
That's illegal.
illegal. That's an error. But it's a common extension. Okay. So both Clang and GCC allow that. Okay, unless you explicitly turn it off. Okay.
Visual Studio, Intel, pretty much everything.
Yeah, pretty much everybody allows that. Well, that means that I can declare an empty type that's an empty array. And how big is that empty? 0. Okay.
Oops. Yes.
Okay. So I can have an array of 2 empties, and the address of those 2 objects are equal. Okay. What's that? It's fine. They're not in the struct. Okay? Yes. By some logic, that's okay. Okay. I can write this piece of code. I can have a void function returning void, and I can say return an instance of void. That is allowed. Okay. But can I declare a void x and assign the result of that function into it? No. Okay. But void star is a pointer to anything. Okay. This piece of code. What will it print in the event of a failure? Anybody? Basic exception guarantee, it's valid but unspecified. Could print anything, but it shouldn't crash. Okay. What if we do this? If we move x into y, move from object x is valid, okay, but unspecified. Okay. So good code has meaning, right? What do I mean by meaning? Meaning means it has a correspondence to an entity. It's something that's specified. It's something that's defined. Okay? So here, the meaning of our predicate, okay, is its relationship to the function. Okay? That predicate represents the precondition to that function. It's outside the code. Which leaves us with categories of nothingness. Right? We have the absence of something. Right? We have 0, the empty set, an empty range, void. These are all the absence of something. And then we have the absence of meaning. Nan is a token to say this doesn't mean anything. Okay? Undefined in the standard is has no meaning. Indeterminate is has no meaning. Okay. So if we wanted to deal with these things consistently, how would we define these same operations? Right? So the terminology that Alex Stepanov uses in Elements of Programming would be partially formed. That int x has no meaning, which means it's partially formed. Which means there's only 2 things that we can do to something that's partially formed. We can ascribe meaning to it through assignment, okay, where it's on the left-hand side of the assignment, or we can get rid of it, okay? So this has no meaning, so those should be the only two valid operations on int x. Okay. This guy, undefined behavior is correct because we're reading from a meaningless value. Okay. This guy, I'm actually OK with infinity because it's an approximation of overflow, which is what we have here. Double x, 0 over 0. Nan, it's OK, but undefined behavior would also be OK. Because we're assigning from something that's meaningless. Okay? The reason why floating point arithmetic introduced nan is so that you could do a stream of calculations, not checking the error at every stage, and just check to see if you've got a nan at the end. Because almost anything you do with a nan just yields a nan. And so it's a way of throwing in an exception or doing error handling. Okay. It would be nice if there was some way in the language. I don't think that we could just change the language to say the size of an empty struct is 0, okay, without going back in time in a time machine. There's just too much code. But it would be nice if we could say that I really mean this thing to be of 0 size. So inherit from void would be one way to do that. And then that would give us an empty size. And the universe doesn't unravel when you do that. And we know the universe doesn't unravel when you have empty size structs because we can have empty size arrays and the universe doesn't unravel. Okay? So this guy, I think that should be OK in the language, right? It's common practice. We should just standardize it. So, which makes that OK. And I'm even OK with that. Okay. So this, I think, should continue to be OK. Right? But so should this. Okay? And void star is OK as well. Okay, this. I actually have a bit of a problem with the basic exception guarantee, right? Which is, I don't think that it should be legal to read from x.size. So in fact, I want it to be, if not outright banned, to at least be undefined behavior. So the reason for that is if it's undefined behavior, then my compiler can legitimately flag it and say, no, don't do that. But what you're doing there is you're reading a value with no meaning. Okay? And you shouldn't do that. And there's no token there to say that this thing has no meaning, which means your meaningless value is likely to propagate throughout your application. Same thing here, right? I don't think there's any real such thing as valid but unspecified, right? Unspecified means it's not valid. It has no meaning. Right? So x becomes partially formed. And that makes you wonder. Take chicken, for example. My movie quotes here. So fairly recently on the C++ standard reflector, somebody proposed a clone pointer type. I guess they took it to a meeting. I wasn't even present for this, but folks told him, your clone pointer doesn't work. It violates the rules. You want to understand more, go talk to Sean. And I'm not even on the standards committee, so it was an odd response. So I got this email saying, hey, I'm trying to put together this proposal, and it's wrong. It's Jonathan Coe who put the proposal together. And he said, well, it's relatively simple what I want to do. I want to introduce a new smart pointer type clone pointer that's just like unique pointer, okay, but with two additional operations. Copy and assignment that copy the object that's pointed to. Okay? It seems relatively simple, right? So here's a very short example implementation that would satisfy that. Okay, so when we copy a clone pointer, it copies what the clone pointer points to, and when we assign a clone pointer, it assigns what the clone pointer points to. Okay, So there was much more to the class than this, but this is what it boils down to. Okay. So to understand why this is wrong, we have to understand what is copy. Well, copying an object creates a new object that's equal to and logically disjoint from the original. That's the semantics of copy. That's the semantics of we copy things in the English language, right? Right? So it's the semantics of every copy within the standard library. So if we create a copy of B into A, then that means that A is equal to B. Okay? And if we create a copy of B into A and then we modify B, then that means that A does not equal to B, is not equal to B. Okay? So that's what we mean, which are logically equal but disjoint. So what happens with a clone pointer? Okay. Well, if we make a copy of B into A, it copies the things that the pointer points to. But since it was just like unique pointer, if we compare them, we're just comparing the pointers. And now the pointers are not equal. Okay. So copies are not equal. That's a contradiction. Okay. It's also very dangerous. The reason why it's dangerous is because your compiler is allowed to elide copies, right? Which means your compiler, if it can determine that these were copies, so therefore the result is equal to some original source, it can say, well, we'll just reuse the original source. We don't even have to make the copies. We can get rid of it. Your compiler can do that. Okay? But that's under the assumption that the results are equivalent. Okay. So well, what's one thing that we could do here? We can amend our specification. Okay? So we're going to say that making a copy is as if they were equal, doing a deep comparison. But since we don't actually have a deep comparison, we're just not going to implement equal equal. Okay? So we're not going to change the code at all. We're just going to change the specification. Oh, I'm sorry. We are going to change the code because we're going to remove the equal operator on our unique pointer. So we're going to take it out. OK, so that resolves that. Well, what's the next thing that we have? Well, what is a pointer, right? This thing's called a clone pointer. What is a pointer? Well, a pointer is an object that refers to another object via dereference operation. Two pointers are equal if they refer to the same instance of an object, which means that A is equal to B if the address of dereferencing A is equal to the address of dereferencing B. OK, so now we have our clone pointer, A equals B. That implies A equal to B, which implies that it's a deep copy, okay, which would imply that we could assert that, but that wouldn't be right because we actually copied the object. So the address of the two objects after the copy are not equal. So we're going to have to amend our thing again. Okay, so clone pointer is not a pointer because it does copy. So we're going to rename it to be indirect. Okay? So what is const? Right? Well, const is a type qualifier. And an object accessed through a const reference may not be modified. Right? So if I have a const t, A, assigned from B, and then I have some operation that's reading A, then that implies that A is still equal to B. And modifying A is not allowed. Okay? That's what const means. Okay? But with my indirect, as I currently have it defined, I can jump down and define read to be a modify. Okay? And that's going to end up here where I have a const indirect A is equal to B. I read from A. It modifies the thing that when A was a pointer pointed to. And so we violated our A equal B. Okay. So that means that const has to propagate from the local part to the remote part of our pointer type. Okay. So that means we need to overload our gets. Okay. So copy implies const propagation. Right? It does. This is why if I have a vector of integers in C++, and you know that all of those integers are sitting out in the heap somewhere, if I have a const vector of integers, then those ints stored within it are const also, right? That's const propagation. Right? And that's implied by the fact that I can copy my vector. Is where that rule comes from. Now there's an alternative specification. Right? At this point, you might say, well, now we've got this new indirect type that doesn't do const propagation. It doesn't define operator equal. It does the copy of deep things. It's not really what I wanted to begin with. What I wanted was a clone pointer. OK? Well, there's another way to do it. You can say, let's define our clone pointer that is just like unique pointer, but with one additional operation, clone, that makes a copy of the thing that's pointed to. So this would be an alternative definition, right? Right? Don't try to redefine the meaning of the standard operations that have well-defined semantics. Introduce a new operation that has the semantics you want. Right? So another approach to solve the problem. So the actual approach taken has been to write a whole new proposal on indirect and introduce an indirect type. So what's in the box? Okay. So it would be nice if we could write code such that we know that every object had meaning at every state in our system. Okay? It would be nice if we didn't have to deal with things that were undefined or unspecified or indeterminate, right? Or partially formed, right? These are all different names for has no meaning, right? Right? And here's a paradox for you, right? Every permutation is defined as a set of cycles. Okay, right? You move objects from one location to another. Where that object lands, you move it someplace else. So if I'm going to perform a permutation, at some point I need to remove my object from my sequence. Right? Right? Temporarily, and then I'm going to move other things back around. So what's in the box? What's where it used to be? Okay. Well, I've got two choices. I can put nothing in the box, in which case this is no longer a valid sequence of objects. Okay. And it's an unsafe operation. Or I can put something in the box, in which case I'm doing an unnecessary write to put an object in that location, and my code is inefficient. Okay? Those are the only two options. Right? So this is from Alex Stepanov's book, Elements of Programming. Right? So there's a duality between transformations and the corresponding actions. An action is definable in terms of a transformation and vice versa. What does this mean? So, okay, it means that we can take a function, right, a pure function that modifies x and returns x, and we can write it in terms of an action that just modifies its argument, okay, and vice versa. Right? So there's a duality there, right? And one or the other of these representations might be more efficient, right? So when you talk about functional programming, which tries to achieve safety everywhere, and people keep saying, well, functional programming keeps getting faster, it's forever vexed by our permutation paradox, right? The reason why I can't have an array in a purely functional system, okay, and do mutable operations on my array is because it's unsafe. But a number of important operations like sort are provably most efficient if I do them in place. Okay. But that raises an interesting question. If we can do a transformation between an action and a function, okay, then what's purity? What does purity really mean? And I'm stealing this section of my talk from Andrei Alexandrescu, because he did some recent work on D that I thought was quite good. So textbook purity to implement something like Factorial would require tail recursion. Okay? So if we had tail recursion in C++, which we don't, so this is going to create n memory, order n memory allocations. It's called p-space allocations because we're just going to keep going up the stack. But if we had tail recursion, a compiler that would optimize that, if we were programming in Scheme or Lisp or a functional language, Haskell, then this is how we would write Factorial. And this is your classical textbook, completely pure implementation of Factorial. And it's a very unnatural way because in order to get the tail recursion, we have to write this helper class. Okay? But in mathematics, you'll see Factorial defined typically in what appears to be iteration, right? From k equals 1 to n, take the product of k. Okay? So this is the natural representation of Factorial. Is this any less pure than the other one? Right? So I would contend, Andre contends, that the definition of a pure function is a function that always returns the same result for the same arguments, right? So there's no reading and writing of global variables. Global constants are okay. There's no calling of an impure function, right? Which means there's no I/O in there. But local transient state inside the function may be modified. That's completely fine. Okay? And in fact, in the D language now, they've implemented this notion of purity, right? And it's quite effective to help prove out a system. So further, you can take it even further and say anything reachable from the arguments may be modified. Okay? Why do I say that? Because we know that we can always transform an action, which is modifying your arguments, right, to a function transformation. Right? We know that that's always there. Right? So that's a valid thing to do, which means std sort is pure. Right? And so are all the other permutation algorithms in STL. Right? So this is a non-textbook, relaxed view of functional purity. Right? And it's not that I'm lazy, I just don't care. So, good code has meaning. Good code is also efficient. Right? What do we mean by efficiency? Maximum effect with minimum resources. Right? So, efficiency is affected by your choice of data structures and algorithms and choice of what to optimize for. Right? So, let's take a look at an algorithm here. This is std reverse that does pairwise swap. Okay, so that's how the algorithm looks. Okay. Now, in the standard, there's no reverse for just forward iterators, right? Right? But I contend that there should be, right? Why? Because there's an algorithm here. This is pulled from Elements of Programming, which is O n log n behavior, which is a reasonable time constraint, right? There are a lot of algorithms that I don't think should exist in the standard, which do not come directly from the old STL, where they have quadratic behavior, which I think is horrible, even if it's documented to be quadratic. But this has reasonable time complexity, right? So how many people knew that you could reverse a sequence with just forward iterators, only marching forward, and do it in a reasonable amount of time? So let's take a look at how this actually works. Right? So it's a divide and conquer implementation. So that's how we step through. And that reversed our whole sequence. Okay? Yay. It's hard to do animations like that in slides. So how does this affect when I'm working on the code system? So this is Microsoft Word again, and we've got a piece of text selected, right? So a naive thinking about a structure for something like this is we've got some current document, and a document is just a big array of characters, and we have a selection in that document, right? But when we're looking at a system, What we're concerned with is all of the operations that we can do on that selection, right? And we want not just constant time, constant in quotes here, constant time indexing into it, but we also want constant time insert into it, okay? And constant time erase into it, right? So as soon as you start to put constraints on something like that, you immediately fall out of things like, well, if it were a list, I could have constant time insert, but I couldn't have constant time indexing. And if it were a vector, I could have constant time indexing, but not constant time insert, right? And so you immediately get into some kind of more sophisticated data structure, right? So in this case, I have no idea how Word is written, but if I were writing Word, I would be looking at using something like a rope, okay, which is a tree representation for a sequence, and it gives me log n operations, okay, for both indexing and insert. And I think a lot of people, especially younger programmers, have a bad idea of what the difference is between constant time, log n time, and linear time. These are not points on a scale, right? Log n is effectively k with just a bigger k, right? You're never going to end up with a problem that doesn't fit in 64 bits of k. So a log n problem is going to be 64 bits. Even if you're looking at a log n problem for particles in the universe, you're talking about a number on the order of 128. Okay, so log n is effectively constant time. Okay, so we can talk about what it means to have a type that's efficient, right? To understand that, we first, not an operation, but a type, right? So first we have to understand that a type is complete if there's a set of basis operations provided on the type that does allow us to construct and operate on any valid representable value, right? So my integer is complete if I got a set of operations that will let me get from one integer to any other integer. Okay? That's a complete type. Okay? And a type is efficient if the set of basis operations allow me to get to allow for any valid operation to be performed in the most efficient way possible, right? Which means that I can get from point A to point B in the most efficient way possible. That I have a sufficient set of basis operations on my type to do that. Okay? So by simply making all the data members public, you provide, by definition, an efficient basis. Okay? It means that I can get from anywhere to anywhere within my space in the minimal number of operations. Okay? However, I've failed to protect the invariance of my type, which means that I can also get to any valid point within my space just as efficiently. Okay? So std move is both an unsafe, right? Why unsafe? Because it strips the meaning off the value on the right-hand side, and inefficient operation. Why inefficient? Because it requires that I leave the item that was moved from in a valid but unspecified state, okay? Which means I need to write something back into that object. Okay? So a lot of people hear that, and I've had these huge arguments where they say, Sean says std move is bad. I didn't say std move is bad. Okay? I said something very precise. It's unsafe and it's inefficient. Okay? So, okay, I don't smoke, I don't drink, I recycle. What does that mean? Good code is reusable. Okay? Applicable in multiple problems and general in purpose. So, it doesn't mean that good code has to be generic. Good code can be incredibly concrete, okay, but of general use, like numeric algorithms, okay, UTF conversions, things like that. Okay, so it can be generic when the algorithm is useful with different models, but sometimes it's faster to convert from one model to another, do the operation in that, right? I've seen people do things like oh, I will write an any iterator. This I think actually started in my group in STLab. We did an experiment to say, could we write an any iterator that would kind of hold any iterator at runtime polymorphically? So it's an interesting mental exercise, but it also turns out that 99% of the time, if you were going to write an algorithm using an iterator, you would be better off taking all of your data, copying it into a vector, doing the algorithm on the vector, and putting it back. Okay? Okay, so that's what I mean. Sometimes it's just faster to convert from one model to another. Okay, and we runtime dispatch when types are not known at compile time. So that's what for reusable. We want to minimize client dependencies and intrusive requirements and separate our data structures from our algorithms. One of my pet peeves is what came out of object-oriented programming, which is the proliferation of string classes. Right? People do not write algorithms that operate on strings. They find when the string class that they're using needs another operation, they write their own string class. And so every single project that I work on has at least one, if not a half a dozen, string classes. Right? So stop that. Okay? So this is an algorithm that's in the Adobe source libraries, which is to copy UTF data. Okay, now it can do a conversion during the copy, so it can copy UTF-8 to UTF-16, or 16 to 8, or 8 to 32, or 32 to 16, right? It depends upon the size of the data types. So I can call it like this, which is to say, given a UTF-8 string, I want to copy it into a vector of UN16 data, and so I can say copy UTF to UN16 types, and begin stir, end stir, back inserter. Okay. Now this code does not care whether or not I'm representing my UTF-8 data as a car, or an unsigned car, or a signed car, which are all have slightly different meanings, or whether or not my UTF-16 data is a UN16 type, or a wide car, if a wide car happens to be 16 bits on your machine. Or what your actual types are, or whether or not it's reading from a string, or a vector, or a list, or a stream, right? It's completely independent, right? So write algorithms and don't keep writing more methods on your classes. You mean we're in the future. So this quote comes from John Bentley, and this is kind of the downside of my talk, but it's a bit of a challenge here. So this is from the book Programming Pearls, 1986. So we're now more than 30 years past the publication of this. And what John Bentley was talking about here was he assigned a problem a binary search. In fact, it's the same lower bound problem that we saw at the very beginning of this talk, to professional programmers at Bell Labs and IBM. So these were not bad programmers. And he gave them a couple of hours to convert the description of binary search into a programming language of their choice. High-level pseudocode was fine. And 90% of the programmers found bugs in their programs after they thought they were done. And John wasn't always convinced of the correctness of code where no bugs were found. So this is from 31 years ago, and I would hope that by today, that if I gave everybody in this room the same problem that John gave, that everybody here would pass it with flying colors. But sadly, I know that that's not the case. And the reason why I know that that's not the case is because for the last 23, 24 years, for longer than I've been on the Photoshop team, John's problem, roughly in its original form, has been a take-home test for everybody who interviews on the Photoshop team. So if you want to join the Photoshop team, you get to a point in the interview process where they give you a written description of a binary search and say, take this home, take as much time as you need, but keep in mind if you take too long, we might hire somebody else. Write a piece of code, language of your choice. Okay, you can write in Fortran or Lua or Scheme, I don't care, to solve the problem. And write an argument as to why you believe your code is correct. Very few people pass this test. So very few. I would say it is far less than 1 in 10, and it depends on the seniority of people we're looking for. But it's almost universal. It's like probably 1% of new grads pass it, and less than 10% of experienced engineers pass it. Okay. And this would be an acceptable answer. It doesn't have to be generic code. We're just talking about an array of ints. So this would be an acceptable answer to the problem. This is very good. So that's the size of problem we're looking at. Right. But I do see signs of hope. I've mentioned Elements of Programming. I think that that's a great kind of foundational book that the computer science needed, and I'm glad it's being taught now at a couple universities. I'd like to see it being taught in more places. I think getting concepts into C++ is important. So when I first did these slides, it said, and concepts are in C++. And that was premature. Yep. Let's see. I see an increased interest in new languages and formalisms, and I think that that's a good thing. I especially see this surprisingly on the JavaScript side of the world, where there's a lot of interesting language work going in on the JavaScript side of the world with transpilers. I see a renewed interest in CSP, which is Tony Hoare's book from the 1970s at this point. What's that?
Does actors and stuff like that use the word actors?
I don't think he used actors, so pretty sure not.
Okay.
Okay, but it's basically a calculus for thinking about how you program concurrent systems. So we see renewed interest in functional programming ideas, which even though I somewhat slam them here, I think the ideas are important. And I'm seeing a rise of reactive programming and functional reactive programming, again, largely but not exclusively in the JavaScript space. And a lot of this gets pushed in the JavaScript space because people are trying to do amazing things inside the browser with a heavily crippled and single-threaded language. So they're charting some new ground. Okay. So I tend to continue on my work. I've had this ongoing collaboration with Jaakko Järve, who's now at in Finland. And I'm drawing a blank on the university, and that's horrible. He was at Texas A&M with Björn Strustrup, so we've been publishing papers. Calling out some papers here because they're kind of in the realm of user interfaces and how you construct applications, but we've done a lot of interesting work. That's the link to my website. There's two links there. One is to where all my papers and presentations are, and another is to where a bunch of my code is, so you can find more information about me there. So in conclusion, I think we should all go write better code, right? And that's the end of my talk.
So we have plenty of time for questions, but we also have to feed Sean at some point.
Yeah, I'll eat whenever, so you can ask me questions. Question back here.
You mentioned that it would be unsafe and inefficient.
Yes.
Just like become an alternative.
I wrote a paper which you can find on the web, which is titled "A Non-Proposal for Destructive Move," and before STD Move was standardized, I had something very similar to how STD Move works that relied on return value optimization on the compiler, which is implemented in pretty much every compiler.
It's now, we now apply.
And now required. So yeah. So in fact, I argued with the standards committee that we shouldn't have R value references, but we should just mandate RVO because it gives you 90% of the win with 0 of the complexity. But that didn't happen. but the idea of a destructive move is having a move where after the move, the object that's been moved from is effectively out of scope, okay, and is gone, is destructed for all purposes. The closest thing to it that I've seen, well, that's not quite true. There's some work being done in Rust, the Rust language, that's destructive move, and there's a work of all places in Objective-C, but it also carries into Swift, where an object basically falls out of scope at last use. And in Objective-C, Objective-C has something called automatic reference counting, which is a form of just smart pointers. It means that the last use of your smart pointer, you don't have to kick the ref count up and down. It's the equivalent of a move on the last use, and after that, the smart pointer is just out of scope. Okay. Doing that in C++, though, if you said that objects at last use just could be destructed by the compiler and were gone, would be a massive change to the language, right? Think about all the places where you do things like take a mutex lock, and you say, as long as my lock is in scope, then I hold the lock. Well, if the lock destructed as soon as your last use, which was construction, you would be very unhappy. Okay. So the reason why specifically I titled it a non-proposal was for two reasons. One is I don't think it's particularly doable inside the C++ language. The other thing is I don't think the benefits are sufficient to warrant the changes in the complexity if you did go after doing it, right? So is it inefficient? Yes, it's inefficient. How inefficient? It's costing you typically one additional word gets written back, okay? Most of the time you can live with that, right? I think there's been some proposals to do like a library form of unsafe move, so at least you could do like an unsafe move in the permutation algorithms. Even there, I don't think it's worth it. In order to utilize it, it requires you have yet another constructor on your type that can basically suck the guts out of the thing that you're moving and leave the thing that was being moved in a destructed state. So I just don't think it's worth the added complexity for a relatively marginal win, and I would rather see, the compiler guys try to optimize out that marginal win. But if you wanted a safe and efficient move, that's what it would be. Would be after last reference of your object, the object fell out of scope. So safe because I can't use the object anymore, that's now in an undefined state, and efficient because it doesn't require a write back.
So a couple of questions.
Sure.
One's kind of did you actually try compiling your tail recursion example with optimization turned on?
Yeah, I did.
In
So.
my experience, it actually turns into a loop. At least GCC does.
So I was trying with Clang, and no, Clang didn't turn it into a loop.
Yeah.
I was somewhat disappointed.
If you do mutual ones, it's not that
So.
smart, right? But straight tail recursion, like your example, I'm almost certain that's trivial.
Yes. The compiler is allowed to. Unfortunately, it's like the compiler is not required to, and even where compilers do it, they only do it in optimized builds, which then means your debug builds are blowing out the stack, and so.
Whereas functional language is actually required.
Yes.
My more serious question. You didn't mention clarity as being a property of code. Is that because it goes without saying? Is that because it's
No.
not as important as I think, or it falls out naturally from your other principles?
So it's because I actually don't think that clarity, well, I think the clarity of the interface is important. I do not think the clarity of the implementation is important. If you were to write code that is correct, and it's efficient, and it's reusable, then there's almost no reason for anybody to ever go open it up and have to read the thing again. Okay. So
I don't believe that to be
Principle upon which all boost code ever.
yeah. So write perfect code, and then you don't have a
This is your
problem.
experience with code bases?
No, this is not my experience, of course. But here we're talking about ideals, right? So when I talk about ideals, I don't think that readability and clarity of the code is important. Even in production code, where I think it has a fairly high importance, I think if it comes into clarity over correctness or clarity over efficiency or a clarity over completeness, that the other properties win. Okay, and lots of people disagree with me vehemently about that point, but it's it's what it is. So those are kind of the two reasons why I leave it out. It's lower down on the list, and it's off the list if we're just talking about ideals. So, any other questions? Over here.
About your nothing is something, what do you think about the proposal to make void instantiable?
I very much kind of started that whole proposal.
That proposal was started because Matt talked
To me. So I absolutely think that void should be a regular type, and I'm so in favor of it that I would be willing to sacrifice some sacred cows in the C language and break some existing code in order to make void a regular type. Well, I'm somebody who will break code to make things match an ideal, so I do not take the standard library along this, as long as it's a visible breakage, and I think that this would be a visible breakage. If you write things with templates, okay, it is very annoying when you have to provide a specialization of void, and when you're writing a template function and you've got void that somehow creeps in there, then it becomes especially annoying because you can't specialize a template function, which means you have to write your function in terms of a class so you can specialize the class in terms of void. Okay? And so an awful lot of code that I see in Boost, and an awful lot of code that I write, and an awful lot of code in the standard library, there is like almost one complete additional implementation of a large body of code, which is what happens if void is one of the arguments. So not having void treated as a type that you can treat like an int is very annoying. In general, people get hung up on things that represent nothing because they lead to meaningless behavior. Okay? But in mathematics, we've discovered over a few painful thousands of years that you just have to suck it up. That you can't just define zero out of it, right? That dealing with Roman numerals which have no zero is worse than dealing with a numeric system where you have zero. And yes, zero kind of sucks because it leads to these paradoxes, to these unanswerable questions. How many nothings can you fit into no space? Right? That's nonsense, and you can't ask that question if you don't have zero. And I see people who write code where they're like, oh, here's the zero case, throw an exception. And I'm like, no, don't throw an exception, just handle the zero case. One of the most beautiful things in STL is that it's a half open interval on all the ranges, which means you have a natural representation for the empty range. And so you sort an empty range. It doesn't throw an exception. It just doesn't do anything because there was nothing to sort. Right? So if we can deal with zeros consistently, it helps. So I'm very much in favor of void.
What would it break in a C language? Having regular
Yeah.
Function arguments with like function name
Oh,
and
yeah,
here
yeah.
void close
proposed parent.
Yes.
Now a one argument function instead of a no argument function.
Yes. Or I can say I've got a function that takes an int x, a void y, and int z.
What was the proposed size of?
What's that?
You cannot write that at all right now, so you can't break anything.
No, but I can write a function that just takes a single void argument, and that breaks. Okay. So yeah, there's a number of little subtle edges like that.
So would the C++ version of a function that takes a void be different than the C version?
So
If you had this, if you could treat void just like int, then it would be problematic. The proposal that's in the standard is actually kind of split the difference. It's like here's a few more places where you can take void, where you can put void in, and here's the places that are problematic, and so we still leave it out.
Another question.
Sure.
So you prefer invalid to valid but unspecified as a concept.
Yes.
So then my question kind of comes to, but then you said nan is kind of okay, but it seems like nan is exactly the kind of thing where it's invalid, and yet you can assign it, you can move it around, it taints everything it touches.
Yes.
It's okay, but it's only for floating point types?
It's not that it's okay, it's only for floating point types. The difference there compared to, say, a basic exception guarantee on our vector, which is valid but unspecified, and a nan, is that in nan we have a token, okay, for the meaningless state. In the valid but unspecified, we have no token, which means we're potentially just spreading meaninglessness through our application. Okay, so I would rather have the compiler be able to say, no, that's nonsense. I don't care what the standard says. It's still nonsense. Okay, and so you can't do that. Now, if there were a way for you to call std size and it returned the equivalent of a nan, okay, then I would have less problem with it, because now at least I have a token that says this thing is in a meaningless state. There's like a proposal for like an expected type, so I could have like an expected int, where it's like this thing is either an int or it's an error. Okay, so that's a way of taking nan and propagating it through the type system. Okay, so now you have to be very careful with that, though, because a nan, if you look at things like floating point numbers obey a strict weak ordering except for nan. So if I sort a vector of nans, it does worse than propagate my nans around. It ends up crashing my machine, okay? Because I walk past a sentinel because my nan is neither less than nor greater than any other value nor equal to it, right? Right? And so you lay down a sentinel in a typical quicksort, and then you just blow right past that because your sentinel doesn't have the semantics you thought it did. So when people come and say, I'm calling std sort and it crashes, I'm like, you're doing it on doubles and you've got a nan. It's like in 95% of the time, I'm right. Okay.
So it sounds like you don't really like nan and these kinds of things. You stop it at the source.
I would rather stop it at the source. I understand why IEEE kind of went the route that they did, and there is a definite engineering trade-off there. So what I would love for the standard committee to do is when they hit these choices, instead of making up the rules for every individual case that they come across, specify what the general rule is and then try to apply that consistently throughout. So if you want to keep nans in there, you have two exceptions. One is to say, well, we have these rules and we made a historical exception for nan, and so nan follows this way. Or you come up and you say, well, nan is this way because of these properties, and if we ever encounter another case where nan would be meaningful, then we would introduce an expected type and treat it like a nan. Okay? Do one or the other. Don't just keep coming up with a different definition to say that this thing is meaningless and apply the rules differently in every single case.
So with the invalid state stuff, what do you feel about what we ended up doing with variant?
So the question is, what do I think about what ended up with variant? And variant suffers from the problem of I can be assigning into a variant, and I'm assigning a type that wasn't already in the variant. Variant is like a type-safe union of some sort. So I'm assigning into a variant, and it's not the type that's already there, and so I destruct the type that's already there, but then trying to put in my new type, I throw an exception. So now what type is in my variant, right? And the solution was to basically add a flag to turn a variant into a nan, okay? To add a nan state into a variant that this does not represent any type, which gets a little confusing because we already have an optional type, and so now a variant is kind of an optional variant because it's got this additional state. But they try to make the state like, no, it's only for this one case in an error.
We tried really hard to make it hard to use the state.
Yes.
After that,
Okay. The reason why you're in the situation is because you weren't paying attention to the semantics of other operations. So it's things like a move operation should be distinct from copy, and it's distinct because a move operation, right, if I move this from here to there, that does not require additional resources. Therefore, a move cannot fail. Okay, but if you have a move that can fail, then with variant what happens is I can't move the previous value out of the way, try to put the new value in. If that fails, then put my previous value back. Okay, so you run into this situation because a number of other kind of compromises were made that were, in my opinion, bad decisions. If it were me, I would go revisit those and I would say no, right? If you're putting something into a variant, it has to have move, it has to be a regular type, and move has to be no except. And we have to go require that move is no except, which means we have to go fix the Microsoft implementation of set and map. But I'm a nut. You know, that's what I would say. I'm not under any illusion that would actually get through the standards committee. So here the standards committee is like, well, we made this bad chain of decisions and that led us down to this point, and so now we're going to stick an AN in there and patch it. It is what it is, right? Given the constraints, I don't see a better solution that you could get through the standards committee. So it's not the solution that I would pick. But I don't think my solution will get through the standards committee. So, yeah.
So you talked about the asymmetry between the min and the max, and I think Stefanov actually mentioned that in one of his talks where he got that implementation wrong. And I was wondering, did you discover that independently, or did you get it from him? And are there any other examples of this kind of asymmetry coming up besides min and max?
Ooh, off the top of my head, that's a tough one to come up. I mean, it actually does come up frequently where you find you define things asymmetrically, and I just know writing code, I always try to pay attention to like what order are my parameters in, and why are they in that order. Did I come up with this independently? Wow. I don't know. I've got this a wonderful email where at one point I sent an email to Alex and I said, can I quote you on this? And he replied, it was very nice. He said, Sean, you can always quote me whether I said it or not. I think I'm the only person on the planet that has that permission. We worked together really closely for a lot of years, and I think for almost any piece of code, if you asked us both to write the piece of code, we'd probably end up with the same piece of code. So honestly, I don't remember, right? If he made the observation first, or I made the observation first, or it very well could have been somebody in one of Alex's classes who made the observation first. But I'll give Alex credit. So, and Alex would give Pythagoras credit, so that would be the. Any other questions?
We should have a proposal for stable max or something like that.
We don't think we can fix Max.
Yeah, you would have to we've even had the conversation because there's some work that's being done for kind of an STL 2.0, right? And the idea is put it in an additional namespace and fix a lot of the problems in STL. And this is one of those problems where even if you put it in another namespace, changing the definition of it, if it's called from another namespace, is fairly problematic. So I don't think, it's without a time machine, I don't think it's fixable. Right.
It was on all of the implementers' lists of things they would want to fix in a new STL.
Sure.
So, it may
And there's, you asked for another example. So another example would be partition. If you call STL and you do a partition, it puts the guys for which the predicate evaluates to true first, and the guys for which the predicate evaluates false last. Why is that asymmetric? Because 0 comes before 1, so false comes first, and true should come last. So it actually matters when you actually use partition to do things like sort. You find you're almost always negating your predicate because the predicate meaning is inverted from what you actually want it to be. So that would be another case from the standard library.
All right. I think
Okay.
we should thank Sean and let him have some.